All right, in 4.1, we are talking about exponential functions, which are considered non-algebraic and transcendental functions. So an exponential function has this form right here, where a is raised to the power of x. A is greater than 0, and a is not equal to 1. X is a real number. It's not going to be an imaginary. So things to consider: exponential, like if you have f of x equals 1/3 x, okay, that's greater than 0 for sure, and it's a real number. This number right inside is a, and the power is the variable, okay? So the first type of problem you'll see will say evaluate the following at the indicated value of x. So f of x equals 2 to the negative x power. So what you might need to remember, so if I rewrite this, f of x equals 2 to the negative pi power, and I put that in the calculator, and I simply get 0.113. Okay, you're going to round to 3 decimals, not a big deal. So over here, the second one, f of x equals 50e to the 4x. So you may or may not remember this from algebra, but e is an irrational number, and it's approximately 2.718, and it just keeps on repeating. Kind of like pi. We use 3.14 for pi. E is another irrational number that we use often with exponents and logarithms, so you will be seeing that coming up. So this problem has 50e raised to the 4x power. So let's see, this will be 50e to the 4 times 0.02 power, and you're just going to plug that in your calculator. There is a button for e. It's already in the calculator, so you just have to plug it in correctly, and when you get that, you're going to get 54.164. All right, on f, so f of 3/2 is going to be 0.6 raised to the 3/2 power. Okay, so when we calculate all this, we get 0.465. Lastly, f of 1/3 is e raised to the negative 3 times 1/3. So that's really e to the negative 1 power. So I can put an e to the negative 1 power in the calculator, and I get 0.368. All right, it's pretty simple, straightforward. Just plugging things in the calculator. Now from here, we're going to talk about graphing the exponential function. Okay, so the parent function of the exponential looks like this. Okay, you have to think about when x is 0, no matter what a is, anything to the 0 power is 1. So when x is 0, you have this point right here. Okay, it's 0, 1. So my exponential function, parent function, looks like this. Okay, and it's considered a growth function when it looks like this. So you're going to use what you know about exponents to create a table of values and graph the exponential functions and determine the asymptote. Right? So let's just do this a little bit of time. So let's do this. 2 to the negative 2 power. Okay, you may or may not remember what the negative power does, but it basically puts it in the denominator. So 2 squared. So this is 1/4, or 1/4. Okay, and negative 1 power would be 2 to the negative 1, which is 1/2, which is 1/2. 2 to the 0 power, anything to the 0 power is 1. 2 to the first gives me 2. 2 squared gives me 4. And then if I plot these points, 1, 2, 4, at negative 2, I'm very, very close to the y-axis. Negative 1, I'm a little higher. Here I'm at 1. I'm at 2, and then I'm at 4. So you can see what shape our exponential function is going to take. Now, as far as the asymptote, hopefully you know an asymptote is what it approaches, but it doesn't cross. So notice, even when my exponents were negative right here, we didn't go below 0. Nothing is negative in my y column. So that means it's not going to cross that 0 line. So 0 is my asymptote, so I'd say y equals 0. So the next one, look at this. e to the x power. So remember that e is approximately 2.718. Okay. So if I think about this, e to the negative 2 is like 1 over e squared. That I would put in my calculator and get 0.135. E to the negative 1 is 1 over e. Put that in your calculator and you get 0.3788. E to the 0 power is just 1. E to the first is 2.718 or 2.72. E squared is 7.389. Okay, so that's enough to graph. So let's look at this. At negative 2, negative 1, 1 and 0, or 1 and 2. At negative 2, it's a very, very small number, just above the x-axis. At negative 1, it's just a little bit above that. At 0, it's at 1. That's our parent function point. At 1, it's at 2.78. So you can see it's going to be very, very, very steep curve. Very steep curve. So then, look at your asymptote. What is it not crossing? Where's that imaginary line it's not crossing? Well, it's not crossing where y equals 0 again. Okay, where y equals 0. Even with negative exponents, my y values do not come out negative, so it's not going to go below the x-axis. All right, let's do the same thing with the next equation. 3 to the x power. Well, 3 to the negative 2 is 1 over 3 squared, or 1 over 9. 3 to the negative 1 is 1 over 3. 3 to the 0 is 1. 3 to the first is 3. 3 squared is 9. All right, same thing we're going to do again. So 1/9, 1/3, 1, 3, way up here is 9. Okay, you can see that this curve is our curve is very, very steep. So again, consider the asymptote. Where is it not crossing? It's not crossing the x-axis. None of our y values are less than 0. So there's an asymptote there, y equals 0. All right, last but not least, let's look at this, where it's 10 is my a and x is my exponent. So 10 to the negative 2 is 1 over 10 squared, which is 1 over 100. 10 to the negative 1 is 1 over 10. 10 to the 0 is 1. 10 to the first is 10. 10 squared is 100. All right, graph this. Okay. So 1/100th is tiny, tiny. Way up at 10, so this is getting even steeper, okay? Even steeper. But yet again, look, it's not crossing that x-axis. There's an asymptote there. It approaches it, but doesn't cross it. So y equals 0 is my asymptote. So what I want you to notice about these equations is, look, it's just the base and the exponent. Base and exponent, base and exponent. That is true. If that's true, then your asymptote is y equals 0. You're done, okay? And we're going to look at what happens if you add or subtract something to those basic functions and where that changes your asymptote. Okay, so let's look at this. Oh, one more thing to mention to you. What I want you to notice is that the base, whatever the value of the base is, if the base is greater than 1, then it is considered a growth function. So if a is greater than 1, it's considered a growth function. If that a value is less than 1, like a fraction or a decimal, it's considered a decay function. A decay function. So look at my bases. Each of these are greater than 1, right? 2 is greater than 1, E is greater than 1, 3 is greater than 1, 10 is greater than 1. So they all have the general same shape as a growth function going up, okay? And you're going to see what a decay function looks like here in a second. But, okay, look at these guys. There's some fractions in there. Now, just because it's a fraction doesn't always mean it's decay. You look at A. Look at that value in there. If that value is less than 1, then it is a decay. Well, 1/4 is less than 1, so this is considered a decay function. Now, this one is tricky. It looks like it's a decay function, but look at the exponent's negative. When you have a negative exponent, it can take whatever's in the parentheses and flip it upside down. Sometimes that just means putting it in the denominator, but if it's already a fraction, you make it the reciprocal. So this is the same as 4 to the x power. So look at that. That means it's now a growth function. All right? So 5/4, it's a fraction, right? Well, that doesn't, but it's greater than 1. It's more than 1. So this is called a growth function as well. 5/4 here appears to be growth, but it has a negative exponent. So that's the same as 4/5 x. So 4/5 is less than 1. So this is considered a decay function. All right? So let's graph these guys and figure out the asymptotes, okay? So look at this. We said it's 1/4 squared, or to the negative 2. So when I flip it over, it becomes 4 squared, which is 8. 1/4 to the negative 1, which is basically 4 to the first power, is 4. 1/4 to the 0 power, anything to the 0 power is a 1. 1/4 to the first power is 1/4. 1/4 squared, oops, 4, is 1/16. Now, let's graph this. It's doing this. So notice the change in direction. It's going downhill. That's a clue that it's a decay problem. Now, I do want you to notice, where's the asymptote? What line is it not crossing? It's coming very close to it, but it's not crossing. That still is y = 0. All right? Let's try the next one. All right, so we rearranged our function to be 4 to the x power. So it's 4 to the negative 2, which is going to be 1/16. 4 to the negative 1, which is 1/4. 4 to the 0, which is 1. 4 to the first, which is 4, and 4 squared, which is 16. So if we graph these, so here's my growth function. See how these are kind of mirror images of one another. But then, where's the asymptote? What is it not crossing? It is not crossing that x-axis, and that is where y = 0. Okay, let's try the next one. We know it's growth, so it's going to have an upward swing. So 5/4 to the negative 2, to the negative 2 power is going to be 4/5 squared, which is going to be 16/25. Okay. 5/4 to the negative 1, it's just 4/5. 5/4 to the 0 power is 1. 5/4 to the first power is just 5/4. 5/4 squared is 25/16. Again, the asymptote, what is it not crossing? It is not crossing this x-axis, which is also known as y. Next one. 4/5 raised to the x power. So 4/5 raised to the negative 2. Remember, that'll flip it over and square it. So it's going to be 25/16. 4/5 to the negative 1 is 5/4. So that's 1 and 1/4. 4/5 to the 0 is 1. 4/5 to the first is just 4/5. 4/5 squared is 16/25. All right, so let's see what happened this way. We think it's a decay problem. It should look like it's going down. So let's see. So it's a decay curve, right? And then asymptote. Where's the asymptote? What is it approaching but not crossing? Again, it's not crossing the y = 0 line. Right? So will that ever change? Yes, it will, and we're going to get there. All right, so look at this. All right, so we're going to describe the transformation on F that yields the graph of G and graph it by hand. Okay, so let's first graph F. Right now, this function is a little on the tricky side. Okay, you want to think of it as -1 times 6 to the x power. Separate that negative out. Okay, and if you put a 0 in for x, you're going to get 6 to the 0 power, which is 1 times -1. So really, our parent point, it becomes 0, -1. Okay, and because of that negative, it's reflecting over the x-axis. What normally would be going up, like this, gets reflected down. Okay, so if that's our f function, let's think about what are these transformations doing to it. Okay, look at this. Okay, -6x plus 3. What is that plus 3 going to do? Well, it's just going to move it up 3 units. So our point at 0, 1 goes up 3 units, or 0, -1 goes up 3. It goes 1, 2, 3. Other than that, it's going to maintain the same shape. Okay, so at 0, 2. Now, think about this. Think about your asymptotes. Okay, look, it's not going to cross up here where x is 3. And how do I know that? Because it's a plus 3 here. My asymptote is at y = y = 3. Right? So look at number 2. Let's try another one. Here's my graph. 0.4 to the x power. Okay, this one keeps our parent function of 0, 1 just fine. Right? And but it is a decay. It is a decaying graph because that a value right there is less than 1. Okay, it is decay. Now look at our transformed curve. What's going on here? Okay, the x to the -2, that's moving us left to right because it's -2. It's going to move us right 2 units. The -3 is going to move us down 3 units. Okay, so start with that point that we're clear on and go right 2, 1, 2, and down 3, 1, 2, or 1, 2, 3. Okay, so now it's taking that curve and moving it this way. All right, now again, where's my asymptote? Well, what is it approaching? Here's -1, here's -2, here's -3. It's coming very close to it, but not crossing it. So my asymptote is at y = -3. Look at the constant on the end. It always matches the asymptote. Okay, always matches the asymptote. Now let's try this one. 1/4 x, or 1/4 to the x power. It is a decay problem, and x is doing, okay, so here's my f function, right? So look at my equation. What's going to happen? This -x, okay, that is going to reflect it across the y-axis. Okay, it's going to across the y-axis. So this way, okay? If that negative was out front of the 1/4, it would reflect over x, but since it's just with the x value in the equation, it's reflecting over the y. And the +2, hopefully you know that's going to move us up 2 units. So what is that going to look like? Well, let's move this point right here up 2, 1, 2, okay? And if I flip this around, this curve is doing this thing right here, okay? That's my g of x curve. It's crossing where x is 3, right? And then what is it not going to cross? What's that line right there? Well, it's at +2. Y = 2. All right? So you're going to be asked to look at the equations, decide what are the transformations that are happening and things like that, and identify the asymptotes from the equation. It's pretty simple. All right, now, given the following, use a graphing utility to construct a table of values for the function. Then sketch the graph and identify the asymptotes. All right, well, graphing utility is code for a calculator, people. So you're going to use a calculator to help you. You could put this in the y equals line and go to the table if you so wish. So your x and your y. Let's just be consistent and use -2 to +2 as our x values. And when I do that, I'm going to plug those into the calculator just to save time. I'm going to get 1.0123, 1.037, for x is 0. I get 1.111, and this is going to be a 1.333, and where x is 2, I get 2, right? So if I graph that, so my curve is looking like this, all right? Now, asymptote, look at your curve. Where is it not going to cross? It's really not going to cross where x is 1. So my asymptote is y equals 1. Right? So this one, if you wanted to, you could rearrange this so it looks a little more friendly. E to the x minus 5 power plus 2. Okay? Use your calculator to generate your values for your table. When you do, I get these values. 2.001, 2.003, 2.007, 2.018, and 2.049. Now, when I graph this, it's kind of flat, but it is rounding up. But look, it's not crossing right here. And where is that? Well, that is where y equals 2. How do you confirm that? Look at the equation. What is the constant on the end of the equation? It's just 2. Okay, so we talked a lot about exponentials, and this is what you're going to be doing on the homework.